So what can we do? Well, this is where mixture models come in. Mixture models are, one of the real workhorses of the machine learning professional. They are used all over the place, right? So this is very, well knowing about. Mixture models actually solve all the problems of k-means. With mixture models, at least in principle, right, subject to having enough data and all of that. With mixture models, the clusters don't have to be spherical, they don't have to be well separated, they don't have to have similar volumes, and they can have very different numbers of points, right? This sounds like magic, right? Well, if you have a lot of data, a lot of computing power, that magic will become available to you. Otherwise, you might still have, some difficulties. But nevertheless, let's look at what mixture models are and how we learn them, right? So what is a mixture model? A mixture model actually has a whole bunch of desirable features. One of which is it answers brilliantly the question of what is similarity and how do I evaluate the quality of my clustering. If you go with mixture models, all those questions are answered for you. You don't need to worry about them, right? This is a big headache, to avoid. So what is a mixture model? A mixture model is a statistical model for the data. It's actually a type of, probabilistic learning, or statistical learning like we saw, a few weeks ago, when we talked about, these different Bayesian methods and whatnot, right? So a mixture model says that there's a probability distribution over my data points. Right, so think of X as a vector in Rn as a point in this room, right? And what I'm going to assume is what's called a generative model. It's a model of how God creates the data, of how nature generates the data, okay? And the generative model is like this. The way I'm going to generate the data is first, I'm going to pick a cluster. There's say 10 clusters, A, B, C, D, E, and I say, oh, the next data point, you're going to come from cluster B. And then once you've come from cluster B, each cluster has a model, like say a Gaussian distribution or a product of multinomial something. And then I generate the point from that model. Okay? So there's two steps. Picking the component and then picking the data point according to that component. Okay? Now how do I pick the component? This is where my P of Ci comes about. P of Ci is the probability of the ith cluster. For example, if there were 10 and they were all equally likely, the P of Ci's would all be 0.1, okay? But in general, some might be larger and some might be smaller, right? So I can handle clusters of, different, sizes or, densities, okay? And then, so what is my probability of a point is the sum over all clusters of the probability of picking the cluster times the probability of generating that point, given that I'm in that cluster, right? This is our good old rules of probability being applied here. Okay. Remember our example of total probability. What are your chances of getting run over by a car if it's red or blue or if it's red or green? Right? Clusters might be blue, but traffic lights not yet. Okay. Right. So this is what we do. Everybody got this idea? This is really what we're going to be talking about for the next 15 minutes or whatever. Okay. So there are many reasons to like this. One of which is, it is not clear what my objective function should be. It's just the log likelihood of the data, right? Same as when we were doing Bayesian learning or, statistical learning more generally, right? So I have a set of data points. I want to find the clusters and the model for each cluster according to which my data is as likely as possible, right? That's what maximum likelihood means, right? My clustering is likely if it makes my data set likely, okay? So that's good. I now have a nice, measure of, so this is not explicitly a measure of similarity, but implicitly it's going to be, and when we look at some concrete examples, we will see how this works out as a similarity measure. It's also an objective way to evaluate my results, right? Once I've learned the model, right, I can actually do this good old thing from, supervised learning of having a holdout data set, right? And now I take this holdout data set and say, how likely are these points according to my clustering, right? If I have a clustering that was overfitting my data, right, these points will not be very likely according to that clustering. So it's a bad clustering. If I've generated clusters and now my data points tend to be, in the high probability regions, near the centers of the clusters, then it's probably a good clustering. Okay? So this solves the problem of the similarity measure, and it solves the problem of evaluating the quality of my clustering, right? Pretty good. And here's another great advantage of this, is that notice that I didn't specify what this distribution is. Right? I didn't specify what the distribution of the data, given each cluster is. And this is a great thing because what it means is that I can plug anything that I want into here, and the techniques that we're going to see here still apply. So, we're going to see some standard cases of these distributions, but, the higher level lesson here is like, you can define your own convenient distribution for what you want tomorrow. Usually, it can be a simple distribution because the power comes from considering, a whole bunch of these. Okay? So this is actually very general. Like this, in some sense, this is not just one clustering algorithm; it's a whole class of them that could be very different depending on the domain. Okay? So, so this is the general idea. So first of all, let's look at specifically what kinds of models you might have here, right? And then how we might learn them. Okay? So any suggestions for what my, P of x given Ci might be? Anything that comes to mind? Closing your eyes so that you both don't look at the slide and can concentrate. How about
Gaussian?
Yeah, Gaussians, exactly. Right? Each of these guys can just be a good old Gaussian, right? What could be a better model for a cluster than a Gaussian, right? It's like, oh yeah, these points are clumped over here, but then they kind of spread around a little bit, right? Yeah, mixtures of Gaussians. So if you have real data, that is the number one thing, is mixtures of Gaussians. Probably more than 90% of the mixture models that have been built in this world, and there's been a whole lot of them, are mixtures of Gaussians. Okay, so that's actually the case that we're going to focus on, when we look at how this is learned. Okay. Mm-hmm.
Do you remember any examples where it's other distributions?
Yeah. So I'm going to mention another distribution, and then we can talk about even others, right? So the second most common one. So this is mixtures of Gaussians. Probably the second most common one is actually the easiest thing to do for discrete data, and this is to have a naive Bayes model. Remember our good old friend naive Bayes, right? Let's suppose that we have naive Bayes, so the same model, except that the class of the example is never observed, right? It's naive Bayes, but I've hidden the class, right? This is a very natural notion of unsupervised learning, right? It's like supervised learning, except nobody told you what the classes were, right? Nobody gave you the supervision, right? So the next most popular alternative, and the most popular for discrete models is, we're just going to look at this whole thing and think of it as a naive Bayes model. In which case, this P of x given Ci is what? We apply the naive Bayes assumption, right? And it's just the product over all the attributes of the probability of the attribute given the cluster. Okay? The class has become the cluster because it was unknown, but you can still think of it as a class. Okay? Everybody get this? Right? Simple idea. Now we're ready to start fitting things. In fact, there's a classic clustering system called AutoClass. This was developed at NASA initially for clustering stellar objects like stars and galaxies and quasars and whatnot. And then they made it available open source for people to cluster whatever they wanted. And by now people have clustered just about everything using it. So and you can download it and play with it as well. What AutoClass is actually AutoClass can also handle continuous data, and it can handle count data and whatnot. What it does is actually a very nice thing. Is it's naive Bayes with a whole slew of options for which model you use for each x. So if some components are discrete, I could use, say a Bernoulli model for binary x's, a multinomial model for x's that have 10 or, a discrete number of values, maybe a Poisson model for an x that's count data, and a univariate Gaussian model for data that's numeric, right? So it gives you a whole bunch of things to play with. And it also has some Bayesian, techniques for figuring out the number of clusters, right? So it's a very nice thing to have. Okay? So if you want to download the clustering system from the web and play with it, AutoClass is probably a pretty good choice. It's not the latest, greatest clustering algorithm, but on practical terms, if k-means isn't working out for you and you're in a hurry, you might do worse things than just use AutoClass. Okay? So in general, we can have any distribution. So what are some, what's an example of a distribution that's neither naive Bayes nor Gaussian? Anybody have any ideas of, what it might be for some particular domain? Right, this could be the moment where you invent an amazing new machine learning solution to your problem. Or maybe that'll happen when you go home tonight and are like, opening the refrigerator and getting a beer. In the movies they have this expression, the refrigerator door questions. Have you heard of refrigerator door questions? This is like when you go see a movie, right, and the look looks very good to you, and then when you go home and you're opening the refrigerator, you go like, but wait a second, how come he did this after that? It doesn't make any sense, right? And the thing is that Hollywood screenwriters, they don't care about refrigerator or questions, right? They only care about the questions that come to mind when you're there watching the movie, right? And you're like, things are happening very fast, so your brain is just trying to keep up, and you can get away with murder. In fact, another heuristic is that the closer to the finale you're getting and the faster the movie is going, the more implausible things can become. You've probably noticed that, right? But it's like, your brain is getting more and more overloaded, right? So, those phenomena are also relevant to machine learning, right? So what might be the refrigerator door question for you here? It's like, well, let's pick an example of a problem, right? You are trying to cluster visitors to your website, right? E-commerce, right? What I want to know is, how do people travel through my website and how can I cater to them, right? How do I make them go to this product that I want them to buy? How do I, route the right people to the right product? How do I make sure that they don't leave my website, right? What you want to do in that case is you want to cluster people by their sequential behavior. On each page, to which page do they go next, right? So some folks at Microsoft Research, together with a summer intern from, I think, UC Irvine, they built a very nice system that actually clustered, in their case, visitors to the MSN website, but you could apply to other websites as well. They clustered people by their sequential behavior, right? Where do I go from the home page? Where do I go if I start out on the news page, right? I want to cluster people by that. And you know what was the model that they used here? It wasn't Gaussian's because the data wasn't continuous. But it wasn't naive Bayes either, right? Because you're really interested in the sequential behavior. What they used here was a Markov model. Well, we're not covering Markov models here, right? But I mentioned them briefly as they're probabilistic models of sequential behavior. That kind of thing gets used in speech and in compile a lot, right? You can also think of a Markov model as the random choices, right, are which link you follow on each page, right? So there were Markov models before, and there were mixture models, and what they did was a mixture of Markov models, right? So that's the kind of thing that you can do. Okay. Questions about any of this? Okay, but now comes the most interesting question of the whole quarter. How do you learn these things? And the reason this is interesting is that this sounds like a difficult new question, right? But it's not. We already know the answer. So, I want you to give me the answer, and the answer has to be 2 syllables. Give me the answer in 2 syllables. How do we learn mixture models? EM, exactly, see? If you constrain the problem enough, right? This I was also trying to illustrate the problem of constrained optimization, right? If you constrain it to 2 syllables, then the optimization problem is not so hard anymore, right? Because you reduce the space. Well, yes, EM, brilliant answer, right? How did you come up with that?
Well, we have the objective function there to maximize the log likelihood.
Very good. So EM, right, is an algorithm for maximizing log likelihood. In what circumstances?
Assuming you have some function that you need to maximize already.
Okay, but remember, we saw EM apropos of learning Bayesian networks with missing values, right? When there were missing values in the data, right?
Right.
So EM is an algorithm for maximizing likelihood in the presence of missing data, right? So, where's the missing data here? I have my full table of examples, right? It's not like any values of the examples are missing, let's suppose, right? Where's my missing data?
Parameters to the distribution.
No. My parameters are not the missing data. Remember, if I had the missing data, I can infer the parameters and vice versa. But the missing data is like something that's missing in my, data set.
The clusters.
The clusters, exactly. I don't know which cluster each example belongs to. That's my missing data. And now, bingo, we can just apply EM. Right, think of the naive Bayes case, right? The naive Bayes case is actually what makes this, connection clear. Naive Bayes case, the way I introduced it was like, let us just learn a naive Bayes model where the class is always missing, right? Of course, in the Bayesian network case, it was more like, some data points are missing some of the values, right? But nothing says that we can't have a value that is always missing. And that's actually what, naive Bayes mixture models are, right? They're a problem where there's this one variable called the class or the cluster that's always missing. But hey, we can use EM for that. We're going to infer that missing variable, and by inferring that, we can infer the parameters and vice versa. Okay? Did everybody get this? This is the key idea in mixture models: is you can just learn them using EM. Okay, so